Welcome back to ECE 501B. Today we get to start a new chapter and we're learning more and more about, or we're adding more and more detail to this concept of linear algebra. And we've started with vectors and how they span and where you can get to. Then we started talking about linear transformations. We talked about operators, invariant subspaces. Now we are going to add the concept of length and angle with respect to vectors in our vector space. And that's chapter 6, which is talking or dealing with inner product spaces. We'll introduce the concept. Oh, and before I scroll down too far, I just want to remind you that homework 4 is due on Monday evening. So we will meet again, but that will be due that evening on the 19th of October. We'll talk about the concept, the inner product giving us this idea of length and angle. We will discuss the properties or just list the properties of the inner product. Once we have an inner product, we can combine that with our vector space to say now we have an inner product space. That just means we have a vector space, and associated with that vector space we have an inner product. We will look at some examples. We will get into orthogonality. We'll even start thinking about triangles. We'll extend that in the Pythagorean theorem, but now we have an ability to talk about what that means in general terms for these vectors. And beyond that, we'll talk about the Cauchy-Schwarz inequality and the triangle inequality. Again, all of these generalize what you might be familiar with in 2 dimensions or with simple geometry or geometrical shapes. Let's then get started with chapter 6, which is this inner product spaces. And as I said before, this is going to provide us, or provide our vector space, with the concepts of length and angle. Or you could think of another way of thinking of that. Now we can sort of keep track of the distance in our vector space and maybe the closeness or how aligned these vectors might be. And vectors now, again, are these general or very general concepts of elements in our vector space. And those vectors then, what they are, will depend on what our vector space is. Here is, let's say, the definition, or you could even consider it a rule. How are we defining the inner product? The inner product between, so now we need 2 items from our vector space. We need 2 vectors. The inner product between 2 vectors, let's denote those as V and W, and those are coming to us from our vector space V. Let's just agree that we will write those. That inner product between the 2 vectors V and W is written, open bracket, V, comma, W, close bracket. That's how we will represent or write the inner product of 2 vectors, V, comma, W, inside these angled brackets. An inner product rule or an inner product is a rule that takes an ordered pair, and it depends on where you put these vectors in that definition or in that description of the inner product. WV is different than VW in the inner product. An inner product is a rule that takes an ordered pair of vectors there's our ordered pair, V and then W, and it takes those and it collapses them down or creates a scalar in our field of numbers. This inner product is a rule that takes an ordered pair of vectors V and W to a scalar, and that's what we're calling V comma W inside the angled brackets, and that's going to be some scalar in our field of numbers F, which could be real or complex. So that's the rule, but it has to have, this rule has to possess several properties in order for it to be an inner product. But right now, just think of taking two vectors and somehow when we form their inner product, we get a scalar.
Can we say that it's a kind of map from a vector to scalar, not linear map, but a kind of map?
Well, the question was, is it a map from a vector? Now it's two vectors into a scalar. But we will show in a little bit that we could actually make this into a linear function, this concept of an inner product. So we'll get there in a little bit, but right now all we're doing is taking two things from our vector space, two vectors, and with those two vectors, U and V or V and W, that generates a scalar. And it has this inner product has to satisfy the following properties in order for it to be an inner product, and has the following properties. The first property is positivity. That means it always has an upbeat attitude? No. But if you take the inner product of a vector with itself, it's always going to be non-negative for any of the vectors in our vector space. So that's the first property, is positivity. The second property that it needs to possess is definiteness, which means if we again take the inner product of a vector with itself and it equals 0, the only time it's going to equal 0 is when the vector itself is the 0 vector or the 0 element, if and only if V is equal to 0. We also want this inner product to possess or have additivity in the first slot. This bracketed expression has two slots, the left slot and the right slot, and the left slot is slot 1, the right slot is slot 2. That's what we're meaning by the first slot. So the first slot is that slot. That's what I'm meaning by the first slot. And we want additivity in the first slot. Maybe I will erase that so that you don't think it's always going to be V and V. But in this case, what we're meaning is if we have the sum of two vectors in the first slot, then this inner product needs to possess an additivity property in that first slot. So let's say that we now have U and V and a third vector W. Additivity in the first slot just means that we can now take the inner product of U and W and add to that the inner product of V and W. So our additivity is working in the first slot, and this is true for all of these vectors U, V, and W that are in our vector space. So we can now separate that inner product. If we can identify that there's a sum in the first slot, we can pull that sum apart and create two separate inner products, and that's additivity in the first slot. Not only do we have additivity that we want in the first slot, we also want homogeneity in the first slot. What that means is if we have a scaled vector in the first slot, let's say alpha v, where alpha is a scalar and w is in the second slot, homogeneity in the first slot says that that scalar can just be slid outside the inner product of v and w and yield the same answer. And this is true for all scalar alphas. Whoops, why did I say alpha? Let me call it A for now. For all A of our scalars and V and W vectors. And the last property that we want this inner product to possess is actually to have conjugate symmetry. That means if we take V and W, its inner product, that's actually equal to the complex conjugate of the inner product of those two vectors switching slots, or slots interchanged. That's equal to W comma V complex conjugate. And that's true also for all vectors V and W. This may differ a little bit from the textbook, this way I'm denoting the complex conjugate, but I may overbar certain things, and it's maybe not as easy to overbar in my handwritten than it is in a textbook. In the textbook, you're going to find that the author there uses an overbar, so it would be, let's say, V bar to represent the complex conjugate. When you're looking at that, then that's what you need to be thinking when you see a vector that has an overbar. That's now the complex conjugate of that vector. Now, if we restrict our attention to dealing with the real vector space, what do we know is going to happen when we start conjugating things? The conjugate symmetry is really simplified. We don't even have to worry about it if we're dealing with real vector spaces. Note that conjugate symmetry simplifies if our vector space V is a real vector space. And as I hinted in one of the goal statements here, or when we were talking about the goals for today or the objectives, here's some terminology that we will now use. An inner product space is a vector space, let's say V, plus an inner product rule on V. Meaning if we have a vector space and we now put together an inner product rule on that vector space, now we will just refer that combination as an inner product space. That's the terminology that we will use. Let's look at sort of the most common inner product that you're probably already thinking about or familiar with. Let's say that we look at f to the n, and that could be the reals or the complex of, now we have an n vector, and what's an inner product there? Now if we take these two vectors, v and w, and let me actually explicitly identify the coordinates in those vectors. Let's now say that I have v sub 1 as just a coordinate. That's not a vector. v1, v2, and let's say that we have v sub n, since this is an n-dimensional vector. This is the v, and that's in the first slot. And then we have our w vector in the second slot. The inner product of that in Fn is now v1 w1 conjugate. So we take the scalar v1, that's in F, that's either real or complex. w1 is a scalar in F, and we multiply those two coordinate elements that are in the same coordinate of v and w, and we conjugate the second slot's coordinate, plus v2 w2 star v down to v sub n w sub n star. And that's the standard inner product that we will use if nothing is said and somebody says, oh, you have Fn with an inner product. You can probably assume this is the inner product that we are using unless we've stated it differently. Where this is the Euclidean inner product, and with the above rule, or with the inner product, or Euclidean inner product rule, we have that the inner product of v and v will be actually the norm, the 2 norm of v squared. So now the inner product actually allows us to produce a norm in that, with that vector space. This is the squared Euclidean length of the vector v. Now, if we restrict our f to being real, then that's just the traditional dot product that you're used to seeing with vectors. You could now say, oh, this is u dot v. And that's the standard behavior that we actually expect from dealing with geometric vector spaces. Those are the traditional inner products that come to mind when we hear inner product. Let's look at some other inner products that maybe you haven't thought about or seen in the past. So here's some more examples. So now let's look at a few different ones. Let's start with f sub n. So let's say, first let's have an example again in f sub n. Now we could say, okay, we have the same two vectors, v and w, but now let's associate the following inner product. Let's say we have c1, v1, w1 star. So that looks just like we had before, except now we've scaled it by a scalar, c sub 1, plus c sub 2, v2, w2 star, and we'll just continue to scale those pairwise products of coordinates with a scalar c1, c2 through c sub n, which is dependent on the coordinate that we're dealing with. Now we need to make some restrictions on those scalars. We need all of those c sub i's to be positive real. Meaning these are now real scalars that are positive. And that's now forming a different inner product. But you could, now this is like a weighted inner product or a scaled inner product. What about on P sub m? Where this is now nth order polynomials. And here I'm going to actually have two different versions, but I will just look at the second one on a specialized sense or specialized case where I fix little m, or Michigan. Have you seen inner products on polynomials before? Do you have an idea what that might look like? So now let's say that we have p and q. P is an nth order polynomial and q is an nth order polynomial. One inner product could actually be a definite integral. An integral from 0 to 1 where we now have p of x. Again, that's an nth order polynomial as a function of x. Q, but now we need to conjugate q dx. That's one possible inner product with a vector space of nth order polynomials. Suppose I now restrict, let's say now that I want to be on P sub 2, and let me now do that over the reals. So this is sort of my second one on polynomials. Now let me say that I have a vector v and a vector w. It could be p and q, but for whatever reason I went back to v and w. Now I'm going to make that inner product. I'm going to evaluate this function v at -1, or sample v at -1, and multiply that by the polynomial w sampled at the point x equal -1. And I'm going to form that product. I now have two numbers that will be real, and I'll just multiply them together. But then I want to add to that the polynomial v sampled at 0 times w polynomial sampled at 0 plus v1 w1. And you need to sort of pay attention to how many terms I've included in that inner product relative to the order of that polynomial. It's P2, and now I've sampled each of those polynomials at 3 different points in my variable x, or variable t. Let's look at an example. Suppose that we now start with a v, and I'm going to have my argument as t is t plus 1, and suppose that w of t is t squared minus 1. So v and w belong to p sub 2, and I'm assuming I'm dealing with the reals. Let's now look at this second inner product for those particular vectors, v and w. Well, now I need to sample those 2 vectors at 3 different points. I need v at t equal to minus 1, and what's that equal to? So if I plug in minus 1 for t, I better get 0. What's v of 0? And now v of 1. 2. So now I need to do the same thing with my w. What's w evaluated at minus 1? That's 0. What's w evaluated at 0? That's now minus 1. And w evaluated at 1. And now what's my inner product? Now I can take v and w's inner product, multiplying the first 2 together, the middle 2, and the last 2. I now have 0 times 0 plus, whoops, why am I changing my notation? 1 times minus 1 plus 2 times 0. And what's my inner product of the polynomials v and w using this particular inner product? It's just minus 1. Now, here's what I want you to keep track of relative to what I had just said before. Here's sort of some observations. Note, we actually need 3 values, or we need to sample each of those polynomials that were belonging to p sub 2, each of those vectors. We need 3 values or 3 samples in p sub 2 of r to define an inner product. If we went and bumped that up to now P4 in the reals, how many times would we have to sample those 4th order polynomials if we sort of see a pattern developing? We would need to sample the vector or vectors. If we're doing it self, we would need 1 vector. If we're doing it with v and w, we would need the vectors. How many times do we sample those? If we sampled a second order 3 times. Now if we have a fourth order, we need to sample 5. So we've sampled the vector at 5 or more values, and then take the inner product. You could sort of think of now you're populating a fifth order, an R5 vector, and forming the traditional inner product with those 5 samples. Why is that important? Why are we sort of having to sample this a certain number of times? Here is our definition on P sub 2, but now if we go back to the rule or the properties of this inner product, the one that we're sort of playing with or having to satisfy is the second one, the definiteness one. If we didn't sample 3 times on a second order, we could have a 0 result for our inner product when our polynomial is not identically 0. What I'm trying to say, let me try to word that. Otherwise, we could have v comma v equaling 0. Does everybody know that notation? WO without v being identically 0. As an example, suppose that we had a vector that's a second order polynomial over the reals, and maybe we now defined v and w, an inner product, to be, let's say, v of minus 1, w of minus 1 plus, so now we're questioning this, v of 1, w of 1. We're saying, oh, we don't need 3, we just need 2. But we've convinced ourselves, I hope, that we need 3 or more. And this is the reason with this particular example. If we now looked at, let's say we set v of t equal to t squared minus 1, and that was probably my w from before, wasn't it? So now I've switched on us. But now if we had v of t equal to t squared minus 1, this is obviously not equal to the 0. That's identically not 0, but what do we know about our inner product that we've just defined or tried to define here? If we look at v with v, what's v of minus 1? Or what is v of minus 1? 0. And now what's v of 1? And now we have that equal to 0, when in fact the only time it's supposed to equal 0 is when the vector itself is equal to 0. So there's an illustration of why this is not a valid IP, and that's not a IP address or intellectual property, that's an inner product. That's overused, isn't it, IP? What if we looked at another inner product number 1, with vectors in P2? So now let's look at inner product 1, which was this inner product and see what we get with that. And again, let's remind ourselves what we'll be using. Suppose we let v of t in this example be t plus 1 and wt be t squared minus 1. I think that's what we used the last time when we looked at inner product 2, and we ended up with an inner product for those two vectors being minus 1. Let's see what we get for an inner product using inner product rule number 1. Now we're looking at v comma w in the same slots. We haven't changed the slots. This is now the integral from 0 to 1 of v, which is t plus 1, times the conjugate of w, and these are real, so this is now t squared minus 1 dt. First, we have to remember how to multiply polynomials. So now we have t cubed, and now minus t, plus t squared minus 1 dt. Or, integrating each of those terms, we have 1/4 t to the 4th minus 1/2 t squared plus 1/3 t cubed minus t, and we are evaluating that between the limits of 0, 1. That's a definite integral. The 0 limit produces nothing, and we can basically get rid of the t's when we evaluate at 1, and we now have 1/4 minus 1/2 plus 1/3 minus 1. Is that right? So now I have minus 1/4 and minus 2/3. Getting a common denominator, I now have minus 3 and a minus 8, or minus 11/12. And how does that compare with our inner product of v and w from before? Is it equal? Does it equal our inner product that we used using inner product definition number 2? Minus 11/12 doesn't equal minus 1, but we didn't say that an inner product has to produce exactly the same scalar. It just has to satisfy those properties that we had identified before. Now, let's just state an answer to an earlier question, and that was relative to a linear map with respect to these inner products. And remember what we wanted for a linear map. We needed our linear map to have an additivity property and a homogeneity property, and we've actually imposed those on the first slot of our inner product, which means that, notice that first slot in our inner product set of rules exhibits additivity and homogeneity. And those are the two properties we need for a linear map. Which means that if we want this to be a linear map, we need to put our vector in the first slot and put something else in the second slot, but that something else could just be a fixed vector. As long as it's a fixed vector, then we do have a linear map. Thus, for a fixed vector w, then v comma w, that inner product, is in fact a linear map from our vector space F, or v, to the scalars f. So is that inner product an operator? No, because to be an operator, we need the domain and the codomain to be the same, don't we? And now we are going from some vector space V to the scalars F. But we can plug in any vector we want for V, and that will satisfy our linear map properties of additivity and homogeneity. We just need to select a W. And we will maybe use this to our benefit a little bit later. If we need to now have a linear map, we can now use an inner product if our vector space has an inner product on it. Now we can also look at some properties relative to the second slot. Our rules for the inner product focused on the first slot, but when we're deriving things or trying to show things or work with these inner products, it might be nice to know what happens if we have some scaling or addition in the second slot. And here we can also prove certain properties about the second slot. One of those is that we actually have additivity of the second slot. And now how can we show that? Well, let's start with a vector V. No, let's try to do this alphabetically. Start with U, since I'm going to need 3 vectors, and V plus W in the second slot. Now, how can we get these two slots interchanged, or the vectors in the two slots? How can we reverse those? We can take the complex conjugate. So now if we conjugate V plus W, comma U, that's equivalent to what we've just listed. But now we can focus on what's inside the complex conjugate operation, and now we know that we have additivity in the first slot. And now we have our sum happening in the first slot. So that we now have V plus W U complex conjugate, but that's just using the additivity in the first slot. We have V U plus W U conjugate, and the conjugate of a sum is the sum of the conjugates, so that now we have V U conjugate plus W U conjugate. And we can now conjugate those back to get those unconjugated. And if we do that, now we have to reverse the slot, or the vectors in the slots, and now we have UV plus UW, and if we compare that with what we started with, now we can see that in fact what we started with was a sum in the second slot, and it looks like we have additivity of the second slot. We ended up with UV inner product plus UW inner product. Meaning we do enjoy additivity in the second slot. What about if we scaled a vector in the second slot? Now we actually are going to have what will be called conjugate homogeneity. In the second slot. Or here we have, let's say u, and a scaled vector scaled by a in the second slot. Again, if we want to get what's in the second slot in the first slot, we can conjugate that so that now we have AV with u, the conjugate of that. But now we can, what? Play on our homogeneity, the first slot, inside the conjugation operation. And so now we have A with V, the inner product of VU, with all of that conjugated. The conjugate of a product is the product of the conjugates, which now allows us to say we have A star, V comma U star, but V comma U star is just U comma V, so that now we have A star, U comma V. That's the original order that we had before, was UV with A scaling the second slot. Now if we want to pull that scalar out, we have to conjugate it if it's in the second slot. And now you can see how we can slide things in and out and move or simplify additions in the first or second slot because we have additivity. Now that we have this norm, this inner product, we now have a norm. We've actually discussed various norms before. We had the 1 norm, the 2 norm, the 3 norm. We didn't talk about the 4 norm, but we talked about the infinity norm. We've discussed those norms before. But not all of these norms play nicely with inner products. So, for that, what we will say is from here on out, we're going to define the norm as, if I now say the norm of V, I'm going to say, well, that's the positive square root of the inner product of V with itself. So if I now have an inner product on a vector space, and I say, oh, the norm of a vector on that vector space, that's going to mean that I'm taking the positive square root of whatever I'm using as the inner product of that vector with itself, the positive square root. And we can note that if the inner product of V with itself is the Euclidean inner product, then this norm definition, then this is equivalent to our earlier definition of the 2 norm. But we're not going to restrict our inner products to always being the Euclidean inner product, and if we have a different inner product defined on our vector space, that's going to then impose a different norm than the Euclidean norm in that vector space. However, we will use this norm definition with any inner product that we select. Something else to realize is if we looked at the norm of AV squared, what's that equal to? Now we've scaled our vector by a scalar A, and we're looking at the norm squared. If we go back here, the norm squared is just the inner product. And now, what do we have in this? We have AV in the first slot and AV in the second slot. So now we have A conjugate, and if A is a complex number, A times its conjugate gives us the magnitude of that scalar or that complex number squared, and that's now going to be multiplying the norm squared of the original vector V. So if you scale a vector by a scalar A, then you can pull that out of the norm if you want. Now let's talk about orthogonality. Now that we have this idea or this concept of an inner product, we are going to define orthogonality. Where two vectors, let's say V and W, in our vector space V, we will call those or say that those are orthogonal if their inner product is 0. That's the definition of two vectors being orthogonal, is their inner product is 0. Now, if we have two vectors being orthogonal, does it matter which slot those vectors are in? No. So this fact also implies that the inner product of V and W is also 0. So it doesn't matter which slot you put them in, they are both going to yield an inner product of 0. They're going to continue to be orthogonal if slot 1 and slot 2's vectors are orthogonal. You interchange those, you're not going to change their orthogonality properties. That's a good thing. What else can we see with respect to orthogonality? What are some observations? A couple. What if I gave you the 0 vector and said what vectors are orthogonal to the 0 vector? All vectors, right? So now if I give you the 0 vector and I said, what's it orthogonal to? You can say, well, it's orthogonal to everything. So the 0 vector is orthogonal to every vector, which means now if the 0 vector somehow ends up in one of the slots, you know the inner product is 0. The other observation that we can make is the 0 vector is the only vector that is orthogonal to itself. So the 0 vector is the only vector that is orthogonal to itself. The others are going to give you what kind of a result? So the positivity property of this inner product says any other vector that you give me is going to give me a positive result. That non-negative is there to account for v being the zero vector. Let's look at some examples, or another example with how we can use this inner product defining or helping us to define orthogonality. Suppose that we have now, we're playing with second order polynomials over the reals, and suppose we've defined our inner product, v and w, to be the second inner product that we'd defined before. We know we have to sample it how many times? 3. It really doesn't matter where we sample it. We just need to sample it 3. So now let's say that we do it at -1, 0, and +1. Now, it does matter where we sample in terms of what the inner product ends up being, but we need to at least sample it at 3 different places in our argument. So now what we want to do is find a vector, find a w, that is orthogonal using this inner product. What's orthogonal to what depends on the inner product. So find a vector w that is orthogonal with this inner product to, let's say, the polynomial v of t equaling t plus 1. So before today's class, and I said, okay, here's a polynomial, v of t equal to t plus 1, and I'm saying that I'm wanting you to work on the second order polynomials, find a polynomial that's orthogonal to that. Would you have known how to start, or what to do, or what that even means? How do I find a polynomial that's orthogonal to another polynomial? Now you have a strategy. And in this particular example, it's going to depend on the definition or the rule that we're using for our inner product. Now, how are we going to do this? How do we find a w that will be orthogonal to v? What does w look like generically? Where does w live? What's its house look? Well, what does w look like? If we have w now as some generic, but we need to dress it. We need to basically give it some structure. So now we need a quadratic, don't we? We need a t squared, a t, and a t squared. T squared, not a t square. I had a student carrying a t squared in my class the other day, and I got a little nervous. But she's taking a drafting class or some graphics class, so I allowed her to enter with a t square. I thought we were going to have to start doing some drawing. So now we need to create a generic quadratic. So let's just define, or let this second order polynomial w, and I'm just going to throw in some coefficients. Let's say alpha is the coefficient on t squared, beta is the coefficient on t, and gamma is our scalar, or our constant coefficient. And with this inner product, we don't have to integrate, so we don't have to worry about integration, but we do need to examine what our vectors look like at those points that we've agreed to sample it at. Now, what's W evaluated at -1? And again, alpha, beta, and gamma are three unknown coefficients we are trying to find that will guarantee that W is orthogonal to V. Now, if we just evaluate this at -1, we end up with alpha minus beta. Maybe I should have used some variables that I could draw, plus gamma. And what is V of -1? That's 0. Now we need V of 0, or W of 0. That's just gamma. And V of 0 is 1. W of 1 is now alpha plus beta plus gamma. And V of 1 is 2. And what we want or need for orthogonality is we need V and W to be 0. And now we just do this pairwise product with the different V's and W's. We have 0 times alpha minus beta plus gamma. That's the first term in our inner product formula. We have 1 times gamma, and we have 2 times alpha plus beta plus gamma. And we need all of that to equal 0. Well, fortunately, we don't have to include that first term, and now we just have to add gamma, 1 gamma, to the last piece, which has a scaling of 2 on all of those scalars, or we now have 2 alpha plus 2 beta plus 3 gamma is equal to 0. And we need that to be true for alpha, beta, and gamma to give us orthogonality between V and W. Now what do we do? Now we have 3 unknowns in one equation. We have quite a few possibilities, don't we? So in fact, we can find a lot of second-order polynomials that are orthogonal to that particular V of t. We have many possibilities. Suppose that first we let alpha equal 0. Let's just see if we can get rid of the t squared, is what we've done in W. Now that boxed equation says that we need 2 beta plus 3 gamma to equal 0. Again, we have two unknowns in one equation. We can just arbitrarily assign one of those. Suppose we let gamma be 2. Now we need beta to be minus 3. We now have one polynomial that's orthogonal to V. We now can say that W1 of t, which is now beta times t, which is minus 3 times t, plus gamma, which is 2, is in fact orthogonal to V of t equal to 2t plus 1 with the chosen inner product. And now it might be interesting to sort of examine those. These are linear. You could plot those and see what orthogonality for this inner product corresponds to for those V and W's. Let's look at another case. Suppose that we now let the constant term be 0 in W.
Here, if we draw a line like t plus 1 x plus t, so they will not be perpendicular.
So here what I was suggesting is this orthogonality is dependent on our inner product, our definition of inner product. And this orthogonality may not be what you would have expected to see if somebody said, oh, give me a polynomial that's orthogonal to t plus 1, but now these polynomials are quadratics, aren't they? So in general, these are quadratics. These happen to both be linear, but they may not look orthogonal in our normal geometric perspective of orthogonality. But the orthogonality depends on the inner product that we've used or defined. And in this particular case, we were using this for our inner product. And under this inner product, then these two, V and W1, will be orthogonal. So let's look at a different collection of alpha, beta, and gamma and see if that helps or makes it worse as to what we might think is orthogonal to something else. Now we go back to this boxed formula and we set gamma equal to 0, and we will now end up with 2 alpha plus 2 beta plus 3 times 0 equaling 0. Or now we can say that alpha is the negative of beta. And if we just assume that alpha is equal to 1, now we have beta equal to minus 1, and our new quadratic polynomial for W, let's call this W sub 2, is going to be alpha times t squared plus beta, which is minus 1 times t, or this is now t times t minus 1 is now our quadratic that's orthogonal to V of t. So this W sub 2 equaling t times t minus 1 is also orthogonal to V of t that's equal to t plus 1. And we could check that if you wanted. Right? We know how or what that needs to be. We could say, well, what's the check on that? Maybe I don't believe that. Well, if you look at V of minus 1, we've seen that many times. That's 0. V of 0 is 1, and V of 1 is 2. Now we need W sub 2 of minus 1. What is that? That's minus 1 times a minus 2, so it's 2. What's W sub 2 of 0? That's now 0 because we're multiplying by 0. And W sub 2 of 1, 0. And now you can see that we have a 0 scaling all of those so that the inner product of V with W sub 2 is now 0 times 2 plus 1 times 0 plus 2 times 0, or 0. Now let's go into some more geometry. Let's go back to maybe an earlier, and this actually is talked about in one of the resources on the website, the Pythagorean theorem. Let's now look at the Pythagorean theorem in terms of this new understanding maybe that we have with respect to inner products, norms, vector spaces. Here's the Pythagorean theorem. If we have two vectors, if u and v are orthogonal, vectors in our vector space V, then we can actually say that the norm of u plus v squared is now the norm of u squared plus the norm of v squared. So a squared plus b squared is equal to c squared. How can we show that? Well, it's not too difficult now knowing what we have defined as our inner product and the norm inner product relationship. Now we know that u plus v squared, we can write that in terms of an inner product. That's the vector inner product with itself. And the vector here is u plus v. So now we have u plus v in the first slot and u plus v in the second slot, and that's actually the norm squared. But that, if we use additivity of the first slot, which we know is true, we can now say, oh, u inner product with u plus v plus v inner product with u plus v. So this is first slot additivity. And what do we know about the second slot and additivity? Is there any conjugation going on? Do we have to do anything special? No. We have additivity of the second slot. So now we have u with u plus u with v. That's from the first piece. And then we have from the second piece, we have v and u plus v and v. But what was one of the assumptions in our definition of of the Pythagorean theorem? We assume that u and v are orthogonal, and now what do we know about some of these expressions that are in this equation? Now we know that this is 0 by orthogonality. We know this is 0 by orthogonality. And we're left with the inner product of u with itself, but that's just the norm squared. And we have v with itself inner product, and that's simply the norm of v squared. And so that's then the justification of the Pythagorean theorem when two vectors are orthogonal. Now, with that said, did we have to say anything about the inner product that we were using to create those norms? No, we didn't specify anything about the inner product that was being used in that formula for the Pythagorean theorem. Or this result did not depend on the inner product. So now that we have this inner product and orthogonality, we've now found the Pythagorean theorem in terms of these vector space concepts. Now what we want to do is maybe start building up additional resources, and one of those is, can we now decompose a vector into its orthogonal components? So we'll start with orthogonal decomposition next time.